So this is what we did last time. These were our examples that we were going through, and that's what we want to focus on. And what we see here is that we started to do example 7.2, and we only did A. And we had a car that had 1110 kilograms, and it accelerates from 10 meters to 28.6 meters. And we wanted to find the work done by the car. And so what we ended up doing here is that we isolated the car, and because we isolated the car, then the only way the car could accelerate if there was an external force. And what we said the external force was, it had to be the work of friction or the work of the road. So it's the work of the road that changes the speed from V1 to V2. And so a bar diagram shows us that the kinetic energy at 1 plus the external work of friction, that changes it to its final kinetic energy. Once again, K1 and K2 don't mean very much, only the external work means, which is transferred. So then, using the work energy term, we set up that the work of friction does cause this change in kinetic energy, and we ended up calculating that the work of friction was then 398,000 joules. So now I want to get to the second question. And the second question here has to do with the work done by gravity. It says that the lowest point in Death Valley is 85 meters, or negative, it should be negative 85 meters. That's a typo. Or that's negative 282 feet. So again, that's a mistake. This should have a minus sign right there because it's below, or you could say it's 85 meters below sea level. I guess I don't have to put a sign if I clarify that below sea level. The summit of nearby Mount Whitney has an elevation. Again, this is not correct. The reason why that's not correct is that the height of Whitney is actually around 14,000 feet. I believe it's the only 14,000 foot climb in California. So it's actually Whitney Portal, if you know what I'm talking about. So when you climb up to 4,420 meters in elevation change, what is the change in gravitational potential energy of an energetic 65 kilogram hiker who makes it from the floor of Death Valley to the top of Mount Whitney? Again, it's not to the top of Mount Whitney. This is the portal. Okay, so I should clarify that and write that this is, so when I say this, I really mean what's called Whitney Portal. And it is actually quite hard to get permits to go up from Whitney Portal to the top of Mount Whitney. So this, believe it or not, is about a race. So this is actually a running race. It's an ultramarathon, and it's called the Badwater marathon. It's an ultramarathon. So it's the Badwater race. And the Badwater race is 135 miles. And the crazy thing is that when you look at the profile of the race, it looks something like this. And there's some crazy thing that goes on here. So this guy right here is actually, Badwater is in Death Valley. And you can see here is that this is Whitney Portal. So Death Valley, man, it can, there's some races where it's actually 120 degrees. You're running in 120 degrees. which is insane. And people do some really imaginative things here. So they start here, and as they're going through here, and this is where it ends. I mean, I've seen people do coffins of ice. I mean, they change shoes. They, a zillion times. They have a whole team that follows them. It's a very different mentality. So if you look at the details of the race, okay, so here's the details. It turns out that you have a horizontal distance of 135 miles. So in this case, as you are running, right? As you are running, what you're actually doing here, what makes you run, as you already know here, is that you have a normal force. So when you look at this thing, you have a normal force that comes out at an angle. Maybe we should say that's the force of the ground. Maybe we should do that. That's the force of the ground. So then we have to pay attention to two forces. One is the normal force, but we know that that normal force is really counteracting gravity. And the other force is, as you push off, you are doing what? You have to deal with the force of friction. And in this case, we hope that you're only doing static friction. So what you're finding here is that the work against friction, that's going to change your energy. Now, there's a second piece to this. It turns out that there's a vertical distance of 2.8 miles. So when we talk about a vertical distance, there's only one vertical force. So when we're talking about this vertical distance, we have to have a picture that looks vertical like this. And now we have our runner, right? We have our runner, and our runner, wow, this is harder to draw at an angle. Our runner is running vertically. So in this case, we think about the displacement being in that direction, but now the only force that we have to counteract here is gravity, and now we have a displacement that's in the y direction. So it's the work of gravity that we really want to imagine, because the question then reads like as we said here, what is the change in gravitational potential? Gravitational potential is the stored work of gravity, which we then call potential energy. So in this picture here, we're going from minus 85 meters, and then I think they said that the height change was 4220, and then we're going to go to a height of plus 4220 meters. That's what we're paying attention to. So we now know what we're actually doing here. This guy is going to be the negative work of gravity is going to change the energy. And the way we call this energy here is the gravitational potential energy. So let's write that. So from the work energy theorem, here's what we have. We have the negative work of gravity must be the change in gravitational potential. And in this case here, what happens? We see here that as we go, right, we're climbing this. So we could then say that this is a positive work done by our legs or friction. Okay, this is going to be the positive work of friction as we go up. So this is a positive quantity. So our body does positive work, and as a consequence, it increases potential energy. So when I look at my picture, what I'm really seeing here is that I'm seeing a picture that looks something like this. I have a certain amount of gravitational potential. And in this case, it's actually negative. So this is the potential of 1. Now, the question is, why is this negative? Because if this is sea level, and the way they're giving us the numbers, we're saying that that height is 0 here. And we said that associated with this guy is minus 85 meters. Now, we store the work that we do into the gravitational field. So now if I go and I do work here, right? I do work. I then do gravitational work. That gravitational work is a positive quantity, or I could say it's the work of my legs as I go up. And as a consequence, when I combine these two, I have now increased my gravitational potential energy to this point. And once again, I probably should have done this a little bit higher. I think I'm going to change it just to make it a little bit cleaner. Okay, I want to do this a little bit cleaner. So if I go up just one more square, and I go up one more square here, then we can actually make it a little bit cleaner. Because now we can see here that the change, so if this is 1 and this is 1, 2, 3, 4, then you could see here is that this whole quantity right here is the change in gravitational potential energy. And as we said before, this is the only meaningful thing we could talk about with the energy here. So now I can compute that. I know how to do that. So if I look at the change in potential energy, so then the change in gravitational potential energy is in the negative work of gravity. But the negative work of gravity is then going to be the change in gravitational potential energy, and that guy is going to be mg times the height change. And if I look at this, then this will then be a height change goes something like this. We know the mass of the runner is 65 kilograms. And we know that the height change is going to be 4420 minus 85 meters. And that quantity gives us 4505 meters. So then if I plug in my values, I'm going to get 65 kilograms times G times my height change. And when I compute that number, that turns out to be 2.87 times 10 to the 6 joules. Now, I guess the question that we want to ask, So in the metric system, this is what we calculate. And the question we have to ask, what does this number mean? Because we're not used to the units of joules. What does this mean? Well, let's convert to calories, because that seems to make more sense to us. So if I look at the potential energy change, this is going to be 2.87 times 10 to the 6 joules. But then our conversion, it's roughly 4,200 joules for 1 calorie. Let's call it a cal for right now. And if you add that up, that's 683 calories, right? And you got to admit that this is surprisingly a very low value, right? If you have a shake, you would, it's not even close to a shake, right? Shakes can be as much as almost twice as much as this. And the way we really look at this is that you have to remember there is a horizontal distance of 135 miles, while the vertical distance is what was it? I think I said it was 2.8. Yeah, 2.8. This is extremely small height change over 135 miles. So most of the calories are actually used up running horizontal. So most calories are used to go horizontal. My guess here is that, man, you got to be consuming some serious calories. I would guess somewhere between, I don't know. I mean, you'd probably consume, just to make it, right? You would probably consume, is consume 2 M's? I think it is. You would consume, I don't know, somewhere between 15 to 20,000 calories. You would have to be feeding yourself quite a bit in order to make that through. Okay, let's go to the next one here. And this is C. So C involves a spring. So let's focus on this spring right here. And it's asking the question, how far must you stretch a spring with a K constant of 1,000 newtons per meter to store 200 joules of kinetic energy here? So we need to set up a picture to make sure that we're actually getting the right picture. So what I would imagine here is that, suppose we start with an unstretched spring. So what do I mean by that? Well, I imagine that I have my surface here, and now I have my spring attached, and I imagine that this is my block right here. So if this is my block, I'm going to focus on just the center of this block, and I'm going to say that this distance represents the point where the spring force is actually equal to 0. And because of this, I'm going to call this x equal to 0, which is our equilibrium point. So now what I'm going to do is that I'm going to stretch the spring out. So if I stretch this spring out, let's say that I stretch it to some point over here. And so when I go to look at this thing, I'm now taking the rungs and really spreading them out. And so the only thing that I know here is that I have moved this guy some distance, delta x, from here to there. So if I call this, let's call this x1 equal to 0, I'm going to call this x2 exactly the distance that we need in order to get there. So what happens here? I look at this system and I see it has, if I have 0 energy in my spring here, then I'm going to say that initially there is 0 energy in the system. So now what I'm going to do, my work of my hand is then going to do positive work. So in other words, I'm going to come in here and I'm going to do positive work right here. So this is the force of my hand as I pull this guy out in that direction. And I know here that my displacement is in that direction. So that work does positive work. But then all that work that, oh, you know what? I said force of my hand. I should have been more careful, and I should have said the work of my hand. So now that work of my hand does not disappear. It reappears as stored work. And so this is the spring potential at 2, and this was the spring potential at 1. So when we calculate the work, the way we did this here is that we have to talk about the area. And as we have to talk about the area, we said here is that if I had a spring that looks like this, and this is my spring, and this is my distance, what I'm going to do here is that I'm going to do work. How's my work going to go? I'm going to start off at x1 equal to 0, and then I'm going to pull it because the spring force we said was minus kx. So when I look at this, I went all the way to x2. So then if I want to calculate the work done or that got stored in the spring, I have to calculate the area of this triangle. Right? I need this area of this triangle, and you could see that it's half a rectangle. So then, here we go. According to the work energy theorem, right? The work energy theorem then says that the work of my hand is also the negative work of the spring. That work gets stored in the rungs of the spring, and this is equal to the change in the spring potential. So then, from what we showed last time, this would then be 1/2 kx2 squared minus 1/2 kx1 squared. And remember, that's the area of the triangles. Okay? Remember, these are the areas, right? We're calculating areas. So then, because x here, 1 is 0, this whole term goes to 0. So when I look at the spring potential energy, it's 1/2 kx2 squared minus 0, but we're given a couple quantities. One, they tell us that the spring potential energy stored was 200 joules. They tell us that K, the spring constant, was 1,000 newtons per meter. So what we're solving for is what is x2? So let's go solve for this. So now I need to isolate x2 from this equation. And so if I look at that, you could see here is that there's a square root. So when I look at this, the square root of 2, I have to have a square root. So on the left side, you could see that I have the change in the spring potential energy, and I have that 1/2. So if I multiply both sides by 2, I'm going to get 2 delta US. And then I have to divide everything by K, and there's my relationship right there. So now if I just plug in my numbers, I'm going to get 2 times 200 joules. And then my spring constant is going to be 1,000 Newton meters. And then I got to take the square root of this. And when I compute that distance, I get 0.63 meters. And that's the distance of x2. Now, note that x2 is meaningless. Why would I say that x2 is meaningless? If I just give you that this is a point x2, that means nothing. What it means here is that we have to have a reference. And where's our reference? That is our reference. We are pulling it from 0. It's not always 0, though.